Start a new recording here. Okay, so the cross product. The cross product of two vectors is itself, it's a vector. Okay, and of course, we always like to know how it's defined, but it's usually, I mean, its definition arises due to physics. Okay, so let me talk about, hold on here, torque and the cross product. Okay, torque and the cross product. So how many have seen torque maybe in another class? How many have maybe heard of torque or seen torque? Okay, all right, so some of you, all right. So of course, if you ever have to, I want to say this, if you tighten a bolt, you have to use torque, okay, I want to say this the right way. So in the picture here, they have a wrench. Okay, they have a wrench. Okay, and you're applying a force to the wrench, and you're holding the wrench with your hand, and you're moving your hand in the direction of that force, and that's going to cause the wrench to turn counterclockwise. And the effect is that I want to say this the right way, the torque vector goes in the direction of the bolt. So like for instance, I'm trying to recall, how many have heard of like a molly bolt? Like if you tighten a molly bolt, well, how many have tightened a bolt in the wall and the bolt goes through the wall? I guess that's the best explanation I can think of. Like a molly bolt, you're bolting something to a wall like drywall, and you use too much torque, and the bolt kind of penetrates the wall. Diodoth knows what I'm talking about. That's torque. It's going into the wall, the torque vector. And of course, the bigger the wrench you use, well, I'm not expansion anchors, I'm not familiar with that, Christopher, but I guess that's possible. I always think of a molly bolt, but you know, you all know that, like, if you how many have like tightened a bolt into like particle board, and if the bolt goes too tight, the bolt goes through the particle board? That might be another good example. I don't know if you've ever had that happen to you, but the torque goes in to the board, goes in, and of course, the bigger the wrench, the more torque you're using, and the bigger the force, the more torque that's being applied. So torque is dependent, the torque vector is dependent, well, the magnitude of the torque is dependent on the magnitude of your wrench vector R, the magnitude of your force vector F that you're applying, and it's also dependent on the angle, an angle in which you're applying your force. And that angle, I want to be careful here, the angle theta here is shown in the picture in figure 2, but the component of the force that's producing the torque would be the magnitude of your force times the sine of theta, based on the picture, because the force that's perpendicular to the torque, to the wrench, the component of the force that's perpendicular to the wrench is what's causing the wrench to turn, and it's producing torque. So the magnitude of the torque, the magnitude of the torque is equal to the magnitude of the wrench times the component of the force, which is the magnitude of the component of the force. Well, no, that's fine, component of the force. That's the That's the magnitude of the force times the sine of theta. That's the magnitude of your torque, and then the torque vector is equal to the component times that component times the normal vector. And that's how your cross product is defined. How many maybe have seen this in another class? Has anybody seen this the way they develop here in another class? Or but at any rate, the cross product is defined based on this idea of torque. So just like the dot product was defined based on work, the cross product is defined based on torque. And it's comforting to me when I see definitions of dot product and cross product that I know where they evolved from. And so you'll see that the definition of the cross product is analogous to the definition of the torque. Okay? And just like the torque is like if you think of the torque vector going into the wall, well, you're applying, you have a wrench vector and you have a force vector, and the torque vector is perpendicular to the plane that contains the wrench vector and the force vector. So the cross product vector is also perpendicular to the plane that contains the vectors A and B. That's you can see that based on this picture in figure 3. So far are we good? So far are we good? I know this is, we're just kind of discussing it, but sometimes discussing it I think it's good to discuss things, right? That's why you're here. But I try to approach things from a very simple. I use simple approaches, and I like examples. And the torque is a great example. Now the direction of the torque is perpendicular to the plane that contains the wrench vector and the force vector. Well, similarly, the cross product is perpendicular to the plane that contains vectors A and B. But a plane, you have a plane. Well, there can be two vectors perpendicular to a plane, one going up and one going down. So how do you know the direction of the cross product? Well, based on figure 3, you use the right-hand rule. So A cross B, you rotate A into B with you see here using the right hand, the fingers are being curled in from in the direction of A being rotated into B, and your thumb's has to point upward. So A cross B, the direction of the cross product AB is upward, perpendicularly upward, because your thumb is pointing up. What if you were to do B cross A? B cross A. If you went B cross A, so A cross B is not equal to B cross A. Based on the picture, B cross A, your cross product would be, that's right, Eric, inverse, it would be going downward. That's right, Diodath. Okay, so that's simply how we describe a cross. That's how we discuss the cross product in simple terms. Are there any questions so far? Okay, all right. So the book talks, of course, they do a problem where you have a bolt and you're tightening a bolt with a 40 Newton force with a 0.25 meter wrench. find the magnitude of the torque about the center of the bolt. And of course, you're going to use the definition of the magnitude of the torque, which is, in this case, the magnitude of the wrench times the magnitude of the force. So I'm looking right here now in this example, and I'm looking at the figure above. The magnitude of the wrench times the magnitude of the force times the sine of 75 degrees. Okay. And the magnitude of the normal vector, which points into the wall, or in this case, which would point into the paper, the length of the normal vector is 1. Okay, that's the normal vector is a unit vector, and so you'll get 9.66 Newton meters for your torque. Okay, are there any questions on that? All right, and then you can talk about cross products of vectors like I cross J and J cross I. This is example 2, where you talk about cross products of I and J and I. And again, for me, the easiest way to compute the cross product is to use the right-hand rule. So in figure 5, I cross J, if you curl your finger, if you curl maybe, hold on here, maybe, I don't know, let me see how this will work. Let me show my video here. I don't know if you've seen me before. This might be the first time you've seen me. Hello, everybody. I'm Dr. Duty. I don't think you saw me in the last class, but you know, I'm a real person. I'm a real person, so not just a voice. So hello, good to see you all. So in that figure 5, hello Ryan, hello Deodath. In that figure 5, nice to meet you, Christian. Thank you. So in figure 5, you see I'm taking my hand and I'm curling it. I'm curling it from the I vector to the J vector. My thumbs has to point upward. So the cross product of I and J, I cross J, is equal to the K vector. You see how I'm doing that? This is exactly how I would do it in class. But on the other hand, if I cross J into I have to curl my fingers this way. So I bring the J vector towards the I vector, and my thumb's pointing down. So hence J cross I equals negative K vector. Okay, so do you see how that works? And that's how, and then so for the very simple vectors, you can do your cross products using the right-hand rule for very simple cross products.
One moment,
sure,
Professor. So the hand, like our palm, would be around the force, and our fingers would go into the actual object being turned.
Your thumb would go into the wall. Right, your thumb would go into the wall. Your thumb points in the direction of the torque.
Okay.
So like if I'm tightening like this, tightening is counterclockwise, right? When you take a wrench, you got to turn it counterclockwise to tighten a bolt.
Yeah.
Or a screw. So if I'm tightening, take your hand and if you tighten your right hand, it has to be your right hand. Sorry, left-handers, it has to be your right hand. If you curl your fingers in the counterclockwise direction, no, the clockwise direction. Sorry, your thumb's going to point like into the wall. And so, but in this case, you're just you're doing just cross products of simple vectors like J, K, and I. but you almost have to practice it yourself to to see it. But does that kind of answer your question, Ryan?
It
Or
does.
okay, okay, okay. Now I think I mean 9.4. I'm keeping it very simple, and I might try to let you have a little time to work on that 9.4 assignment. But we don't have much time left. But basically, what would you do if you had to compute a cross product of vectors that are not like nice, that aren't nice vectors like I, J, and K? In other words, suppose you have vectors that are given in component form, like A equals 2I minus 3J plus 4K, and B equals 5I plus 6J minus 7K. The way you compute the cross product, there's formulas for cross products, and they use the formulas to derive a rule. And the rule is that if you have a general vector A and a general vector B, the cross product, the components of the cross product vector can be found using this formula. It can be found using this formula, where the components are given by these three components. And if you read on a little bit, they talk about how you could use a determinant, the idea of a determinant, to help you get a cross product. But I'm gonna hold off on that. I'm gonna hold off on that and maybe save that for our next class, because I want to use the remaining 7 minutes for you to work a little bit on this. I think you can. It's linear algebra in a nutshell. That's right, Eric. But if you can use the formula here. So I don't want you to think I try to be a good professor. I definitely want to talk about that determinant formula. But for now, and you can read ahead and learn that, and I think that would be good, because then when I discuss it on a little more on Tuesday, you'll feel comfortable with it. But you can certainly get by with the formula here. You can certainly get by with that for the cross product of A and B. But indeed, look ahead. The problem is this formula is difficult. It can be difficult to remember the formula. Okay, it can be a little difficult to remember those three formulas for the components of the cross product vector. And so they use determinants to help come up with an easier way to get that formula there. And what they do is they take the determinant of a 3x3 matrix, where I, J, and K are figuratively in the first three spots. Okay, so I'll let you study that a little bit. Example 3 will show that to you. But I'm going to stop there for right now, because I want to just let you have a little time to work on 9.4. Let me stop the recording.